I am going to discuss today the application of matrices as operators. I shall especially focus on linear operators and will cover some of the fundamentals about the operators. An operator symbolizes a specific mathematical operation to be performed over the object appearing next to it. When the object is a column vector, the operator is a square matrix. An operator omega acting on a ket vector v transforms it into a new vector v prime. Similarly, an operator delta transforms bra v into bra v prime. The operators are linear if they obey certain rules that I am going to explain now. Take a vector v. Operating it with the operator omega transforms it into v prime. Then take its scalar multiple. Now take the same vector v again. First take its scalar multiple and then operate it with the operator omega. What we have done is reversing the order of action. If this results in the same vector as in the previous case, then the operator involved is linear. If it instead leads to a different vector, then the operator involved is nonlinear in character. This condition for an operator to be linear is stated mathematically as this. Now let us look at the second condition. Take two vectors v and w. Operate both of them with the same operator omega. The resulting vectors are v prime and w prime. Multiply v prime with scalar alpha and multiply w prime with the scalar beta. Take the resultant of these two vectors. Now as an alternate way, take the same vectors v and w again. Now multiply them first with the scalars alpha and beta, then operate them with the operator omega. Finally, take the resultant. We get the same vector as we arrived at by following alternate way. Since the result is same, the operator involved is a linear operator. In case we arrive at a different vector, the operator will be nonlinear. This condition is written in this mathematical expression. An operator must obey these rules to be called as a linear operator. Linear operators follow the same rules for bra vectors also. This was all about linear operators. Now there are some important points regarding operators that must be noted. The simplest linear operator is the identity operator, which is nothing but a unit matrix. When identity operator operates on a vector, the vector does not change. As example, when ket v is operated on by the identity operator, it remains as ket v. Similarly, bra v also remains same when identity operator operates on it. If more than one operator successively operates on a vector, then their ordering matters. Say ket v is successively operated on by omega and omega prime. Alternatively, ket v is first operated by omega prime and then omega. Results in both cases are usually different. The difference between the alternate order products of two operators is known as commutation relation between the operators. Normally, the difference is non-zero. In certain special cases, when the difference is zero, the operators are said to commute. Now, let us define the inverse of an operator. When two operators operating successively on a cat leave it as it is, that is, the operation do not induce any change in the vector, then one operator is the inverse of the other. Now recall here that when identity operator acts on a vector, there is no resulting change in the vector. This implies in the present case that the product of an operator and its inverse is the identity operator. Next, we discuss the adjoint of an operator. Let an operator omega acting on a cat V transforms it to V prime. Then, for the transformation of bra V to bra V prime, there must be an operator to act on bra V. This operator is called as the adjoint of omega. We know that bra V prime can be obtained by performing dagger operation on cat V prime, and cat V prime is obtained by operating omega on cat V. Now, cat V dagger becomes bra V and the operator takes the form omega dagger. Comparing these two relations, we see that the adjoint of an operator omega is omega dagger. Now we look at the matrix element of omega dagger. First, write the ijth element of the matrix omega dagger in the standard bracket form. Omega dagger goes inside bra symbol as omega. Interchange bra and cat vectors with the asterisk sign. Take the operator omega outside the cat symbol. This is in the form of jith element of the matrix omega with the asterisk sign. This shows that rows and columns are interchanged between an operator and its adjoint along with the change of conjugation of the complex numbers. When an operator and its adjoint is the same matrix, it is called Hermitian operator. In the case the adjoint is same but with opposite sign, then it is called anti-Hermitian operator. If the product of an operator and its adjoint is the identity matrix, then the operator is called unitary operator. Recall here that the same relation exists between an operator and its inverse. Hence, it can be concluded that the adjoint of a unitary operator is its inverse. There is a theorem. The statement of the theorem is unitary operators preserve the inner product between the vectors they act on. Take two vectors v and w. Unitary operator u changes v to v prime and w to w prime. We know we can get bra w prime from the dagger operation on cat w prime, and cat w prime is obtained here from the operation of unitary operator on cat W. Cat W dagger becomes bra W. Now let us write the inner product between these vectors W prime and V prime. Write the expression for bra W prime and cat W prime as obtained above. We know U dagger U is identity matrix. This leads to the bracket of W and V. This shows that the inner product of W and V is same as the inner product of W prime as and V prime. Thus, it justifies the theorem. So, in this way, we have discussed some of the important points regarding operators.